In this presentation, our focus is on morphological parsing in the context of recognition grammar. And right from the beginning, I will make the assumption that we are trying to model realistic language comprehension. So the type of recognition grammars that we will be looking at will attempt to create a theory of language comprehension. It is in the context of that type of recognition grammars that the issue or problem of morphological parsing is interesting. But I want to point out that recognition grammars can be used as models of language production, or they could be simply models of linguistic competence only. So this is a kind of special topic. And why this is non-trivial and deserves its own presentation is because we will have to embed the parsing process into the derivational search function. Morphological parsing, like syntactic parsing, involves ambiguities, both lexical and possibly also structural. But that's all about the introduction. Let's go into the topic. And the basic principle starting point is simple. First, we have to have some idea of what morphology is all about, how words are formed, what kind of assembly operations and items and representations are involved when we create complex words like running or sleeping or runner, what the primitive elements are these special, are the assembly operations different from phrasal assembly operations? Is there a separate morphological word formation module? All of these questions, first we have to develop some answer. And in my view, it's the simple starting point here is simply to think of these questions in the context of enumerative grammars or some particular enumerative grammar. And once we have this idea or theory in mind, then in order to apply it in the context of comprehension-based recognition grammar, we will simply reverse engineer that theory. So instead of starting from the primitive parts and assembling them into complex words, we will now have to do the reverse. We have the output available, usually the phonologically complex words, and then we will have to reverse engineer the process so that at the end we will have syntactic phrase structure representations, possibly other manipulations that will constitute the input to semantic interpretation. But so that's in principle what we are going to do, and as I already mentioned, we have to add to this general picture the assumption that the whole process is part of the derivational search function of recognition grammar. But how to begin this? What should we do in the beginning? How to start with something? Well, the first step here is that we need to have, and this is an important part of the initial theory, we will have to develop some preliminary idea of what kind of word boundaries we can have. So one type of boundary is, of course, the word boundary itself, the phonological boundary between, the boundary between two phonological words. Usually in my data sets, and I use the regular convention that I use just the white space to express that. But then when we go inside of words, we need to have a way of representing morphing boundaries, possibly clitic boundaries, possibly compound word boundaries. Perhaps we want to distinguish inflectional morphosyntax from derivational morphosyntax by assuming different boundaries. So we begin from this, and for each boundary we have to develop some special symbol to encode it or represent that. And then we will have a mapping from the phonological words in our data sets into morphological decompositions, which we express by using these boundary symbols. And we will do this, it's best to do this in a way that we can also use these symbols, these boundary symbols already in the dataset if we want, so that we can create productively new words, and we can test our model against attested and non-attested words, as I did already when I illustrated these methods by looking at my Finnish dataset, Finnish word formation datasets, where I simply generated all possible words that can be created from the morpheme set. If you go back to that lecture, you will see that I was expressing the morpheme boundaries by using the hashtag symbol. And then I was talking about the clitic data, and there the clitic boundaries were specified by another symbol. So the first step is that we have a way to map phonological words into their decompositions using these symbols, and then we have a way of reading these symbols directly from the data set. And also the assumption here is, of course, that the full theory would have also a third option, which is that there would be a morphological parser, a separate function that would find out what the morpheme content of the word is by simply looking at the word itself. So that's the third, processing pathway. And again, how you do this, the way how you do this morphological breakdown, it will depend, of course, on your theory. It should be as realistic linguistically as possible, as well argued as possible. However, ultimately, of course, you will be testing your hypothesis against data sets. So initially, it's not so important what do you put into this system. It will be exposed to quite rigorous testing. And then when you have these mappings, and you have a representational format where the word exists in decomposed form. Now, what is the representational format of this stage? It doesn't really matter in the beginning. So I myself, I just use strings. So the input word, the phonological word, is just a string. Ultimately, it's going to be phonological matrix, and then that's mapped into a string, which is its morphological decomposition, the type of decomposition that I think is more or less empirically justified. But nothing prevents one from developing some type of special purpose representational format for just this purpose. And perhaps in the human brain we have some type of special morphological decomposition, though I myself perhaps would be doubtful. Anyway, then once you know how the word has been decomposed, what morphemes there are and what the boundaries are, then it's possible to continue the reverse engineering and map that into a phrase structure, let me say, into grammatical representations or elements in the phrase structure that the derivational search function is creating. So here is in a simple illustration what I'm talking about. The first line here, the first sentence is the input sentence in the data set. The second sentence, where I'm now focusing only on the verb, we ignore the John and Mary. I'm showing just one possible morphological decomposition. And this can be provided in the beginning simply by mapping, direct mapping, especially if we are not so concerned about the lower level steps. And as I pointed out in my theory right from the beginning, it was possible also to provide this second entry in the dataset already, so that I was able to test how different morpheme combinations, ad hoc combinations would work out in this model. And then the third option, if you are interested, you would have a morphological parser doing something like this. Well, here's a question, why wouldn't you want to develop this parser right away? Well, the problem is that it's just an additional layer of complexity that you will have to handle and manage. And unless you are really interested in this lower level processing pathway, it's, I think, safe to ignore. So what I'm doing here, if I use a direct mapping or I'm using this type of words directly in the dataset, I'm simply assuming that there is a morphological parser, because I'm not interested in a lower level morphological parser, because I'm not really interested in that component here. And then there is some mapping into the phrase structure, where these elements that we have here in the decomposed form are mapped into elements that the phrase structure representation can understand. So our theory of phrase structure, the thing that I discussed in the previous presentation, has to contain everything we need here to create these mappings. And what I'm showing here is a system in which morphemes like tense and the verb stem, the admire and t, are mapped into their own primitive heads, primitive constituents, and those are then, they form one complex zero level. Let me be careful. They form a complex constituents which is not phrasal. So in this kind of theory we can have what is called complex heads. They are zero level non-phrasal syntactic constituents which can have several more primitive elements. In this case it's a kind of a synthesis of verb and the tense. And so I'm reverse engineering this mapping simply. And then the third person singular suffix here from the end will be, in this example, will not be mapped into its own head. An could be an agreement head, but rather into a feature inside of other head, shown here as a feature inside of the tense. So we get agreement features inside the tense head. And so this arrows and this operation shows how the elements from the input string are mapped into elements that the phrase structure representation can mapped into the phrase structure representations into syntactic representations. And the point and the problem now is that the interesting point that we have to take into consideration here when we are designing this mapping is that if we look at this third person singular suffix s here, I'm just assuming that it's verbal third person singular suffix, but in English this could be also plural suffix, namely if they are attached to the noun heads. And so very soon we discover that that this whole process involves ambiguities, morphemes which can be interpreted in several ways, and maybe also structural ambiguities. And this means that all of these steps what I'm showing here by these arrows, where these morphemes are going into the syntactic representation, they have to be part of the derivational search function. So that if here I'm reading this S, and if I make the wrong assumption that this is a plural marker, and I then do this operation where I put it inside of the tense, after I do this operation, I have to call the derivational search function recursively again, so that when later we discover that that was a wrong assumption, we can then backtrack to this same stage and then try the second alternative, the verbal first person singular, and put it there, and then we will discover using that option the correct final solution. So right from the beginning, when we are considering this reverse engineered model, the code itself has to be written so that all of these steps can be also backtracked. So I will show soon in this presentation how it works in my current model. That this is not really trivial thing to do. But that is the basic approach how we can develop or let's say make the morphological theory more plausible linguistically. Now let's try to take a look at the implementation of the ideation of the whole system we just described. And unfortunately, this is something that involves extremely non-trivial problems and issues for many reasons. The one reason being that the whole question is empirically so non-trivial, and then when those challenges are combined with the fact that we are working with derivational search functions, so the executive layer puts its own demands on the code. So we end up with a fairly complex, and as I pointed out already, non-trivial. We are facing a highly non-trivial situation. And the implementation, what I'm describing here, is surely just one way to face these challenges. And they reflect my own, they actually reflect two things: my own view on how, let's say, the morphological layer could work, but they also reflect the fact that my own understanding and view is incomplete, and that I also often proceeded with the implementation without anything very clear in my mind, a clear idea. I just wanted to I often just wanted to move on. So in those situations, we all know the result is some kind of ad hoc system. It's not like that anymore. I have put some thought on this, and I will return to this matter when we examine my own current model and the way how I have structured the lexicon. But there is still this legacy code and legacy thinking present. I clearly perceive it. But let's begin with the derivational search function we discussed earlier in an earlier presentation. And so this is the derivational search function for the recognition grammar that we described there. The template is number 4, so this is a template 4, and the project in my GitHub page is templates. So you can find the script there and run it. Now, this script and this derivational search function doesn't do any morphological parsing or morphological work. But what I'm going to do is I'm describing what this simple one does. This could be something you first start with, and then how would we begin to adding the morphological parsing processes into this function. There are several ways. And after that, I think that I will show you how I have structured the lexicon, or some aspects of how I have coded the lexicon in my current model, and there we see how the morphological decomposition works. And then we will conclude by looking at my own current implementation, but I can't go into very much details because there are so many, again, some empirical topics there that it's not so simple to explain in a presentation like this. It would require several presentations and some introduction to the empirical materials first. But let's go into this topic here. So here we had the derivational search function for recognition grammar, which gets a sentence as a list of phonological words and an index which points at some word in that list, showing where which element we are consuming. So here are the input, and the X here is the phrase structure currently in syntactic working memory that we are building. And we build from the words that we have consumed so far. And first is we can omit, we are just checking if we have no words left, so then we go to the post-syntactic function and do the final processing, but we ignore it here. Now what happens in this line is that we take the phonological word from the list of sentences. So we look at the word this index is pointing. And remember, it's the recursive call here that when we move the index, we add one to the index, so we move to the next word. So we take the phonological word we are currently supposed to process, we look into the lexicon and retrieve the corresponding primitive constituent. And then that's y, this element y. And then we merge it into some position at the right edge of the phrase structure in the working memory. And then there are some complications you remember about the copying, but we can ignore these technical issues here. Now what are we assuming here? Now we are assuming that each phonological word we pick up from this sentence, it's mapped by lexicon into a primitive constituent. And this primitive constituent is always merged into the phrase structure in the same way by the operation here. And it then becomes a primitive constituent in the phrase structure that we have in the working memory. But when we start to approach morphological parsing and the topics I discussed earlier in this presentation, this is the assumption we can no longer make. Because now the assumption is that what we have in the input sentence, the phonological words, they don't necessarily map into a primitive constituent that we can always merge in the same way into the phrase structure. Why is this so? Well, because the phonological word can itself decompose into smaller elements. Now let's keep it at that simple level first. I just mentioned that we have additional problems like the clitic boundaries and the prosodic features, and perhaps not all morphemes are mapped in the same way into phrase structure. This is all depending now on our theory of word formation that we are reverse engineering here. But let's simply observe that at least we have to assume that the phonological word itself is decomposed into smaller elements. And this decomposition has to be performed before we can go into do any operations with the phrase structure. In the simplest model, it will be the case that the phonological word can dissolve into several morphemes, suffixes, affixes, critics, so on, prosodic features, which have to be individually processed and assembled into the phrase structure, into working memory. So that's kind of the minimal requirement. Now we could, I just mentioned this option here, we could pre-process the input sentence so that these morphemes or independent parts of the words would not be inside phonological words, but they could be already part of the list itself. So that a sentence like John admires Mary, the admires, the list, this sentence list that we give to this derivational search function could not, perhaps we could pre-process it so that it's not admires, but it would be admire and tens, and then the third person singular suffix. So it would be already broken down before this whole processing begins. If we do it in this way, then here, this function in the lexicon, lexical retrieval, would get each morpheme as its input automatically. And then the lexicon would need to have separate lexical entries for admire as a verb stem, and the tense and the third person singular suffix. And this corresponds, this is one way to implement what I was talking earlier, that we simply presuppose a mapping from phonological words into morphological decompositions. And in this solution, before anything is done, we do this pre-processing. So it's not cyclic. The operation is not cyclic because it's done before anything else. So and it's also not realistic. But it's a shortcut that we could try as a first solution. And this is good also because it allows automatically the backtracking. It makes the backtracking possible because then each morpheme will arrive to the derivational search function for each recursive call as an independent element. And then we can backtrack. There would be a clean backtracking. But notice that we are doing this, we would still be assuming that every morpheme is simply always merge right to the phrase structure. And maybe it is true, I don't know. This would be a simple way if language would all languages would work that way. But at least at beginning, when you begin to work with realistic data set, it just doesn't work like that. That is too simple. Maybe we later find out that it works like that, but with realistic data, it's not really, at present at least, possible. So I add now one layer of complexity into this model, and we keep up with this simplifying assumption that the sentence is pre-processed. So it might be that when you process these items from the list, it might be that you will have to react differently to different kind of morphemes based on the morpheme boundaries, as I already mentioned, or perhaps the lexicon simply recognizes different phonological forms or items differently. It already knows that, okay, this is a clitic and this is something else. So in that situation, this is one way to do it. In that scenario, this function here, which provides us a constituent for corresponding to each item in the input list, there would be a branching, some type of branching where this solution where it's merged to the right edge is perhaps only one option. You could say if there's a prosodic feature, then we do something else. Or if it's an inflectional suffix, we do something else. If it's a clitic, we do something else. So then you would have here branching. And perhaps the lexicon would be the module which is telling which branch you would go. And inside each branch, we have a recursive call, the same recursive call after we do whatever we need to do with that feature. So I think that's quite clear. And my own model has this type of system, so we will look at that later. But what if you don't want to pre-process the whole sentence and you consider that's not realistic? What if you want to do the morphology cyclically, meaning that you actually begin with the sentences as they are in your dataset, as the native speakers see them. And then you want to do the morphological decomposition at the time this word is encountered into input. That's more realistic, and surely this is how it works in reality. So you might want to perhaps we try that system first and ignore this heuristic shortcut. Now the simple idea that comes to mind here is that, okay, we take this phonological word here, and then instead of mapping into constituent, primitive constituent, we have here some type of morphological parser or parsing process which is able to decompose the item. And now you can imagine, and I show you later how it works, a simple mapping again. Imagine that the lexicon contains this kind of decomposition. So it will simply take the phonological word and provide its morphological decomposition in some form, depending on how you ultimately think that words are assembled or created. And then you could create a separate loop, a higher level loop, which would grow. This is the thought that comes to mind. So that then it would, after the decomposition, the system would go into a different mode and start going through all these elements you discovered, sublexical parts. But this encounters the problem, this approach, that how do you do backtracking? Because after you process each of these morphemes in the list that was recovered, you will have to call the derivational search function recursively. But what is the input? How does the next call or the next function, when it goes, knows that you are actually in the middle of processing some word? Remember, so far the input was always the sentence itself, the original sentence where we have phonological words. There are no morphological decompositions there. But this is, of course, technically we can solve this in several ways. One is that we have an additional input to the derivational search function, which is the morphological decomposition we are processing. And then we need some information of which morpheme we are working at. So that's a kind of a possibility. Remember that this is part of the executive layer, so we don't need to be concerned so much how we implement this specific thing, because it's not part of the theory. So you would have some kind of morphological buffer, for example, and that would be an input here, and then the index and sentence would point out to the word, but then when the morphological buffer has some content, we would know that the word we are pointing at is polymorphemic, and it has to be processed each part internally, and then would be the morphological buffer. And perhaps it also has index, or perhaps when we process these morphemes, they are just removed from the buffer. That's one way. Another way would be to modify this sentence when the morphological parser has produced some output. it knows what the constituents inside of the word are. We simply change the input sentence accordingly, so that we put these morphemes there and point the index to the first morpheme we have to process, and the rest are now added. So the sentence gets longer, this so-called sentence. So-called sentence in a way, it's no longer the same sentence as it was in the dataset, of course, because we are adding the morphemes into it. But anyway, this is like the first solution where we pre-process the sentence itself, but now it's cyclic, so it's more realistic at least. It corresponds to the idea that the speaker is seeing, recognizing that the word has certain items. It's this recognition that we are now applying, but in a cyclic way. I do this system myself in this way because I can't believe that this is. I don't believe that there is morphological buffer. I think that there is a simply recognition that the word has, that this item has several linguistical constituents. But be that as it may, that's one way to do it. So then we would have some type of, if we have a complex, this is how I do it. Here, if we encounter a morphological complex word, we do the morphological parsing, and then we simply change the input sentence accordingly where all of these items are there. And then we do a recursive call. And the next call will then see a morpheme that does not have decomposition. So it might be a derivational morpheme or clitic or inflectional morpheme or prosodic feature, whatever. And then that condition is no longer satisfied. It doesn't see morphologically complex word, it sees a simple word, and then it can implement the branching based on what type of element it is. And I like this method. One reason I like this is because I can still use the morphological decompositions in the input data if I want. Because this morphological parser will change, it will recognize that this sequence, this item has a decompositional structure. The lexicon will tell that. But if in my dataset I have this kind of decomposed item, then the same recognition algorithm will also notify, all right, this is morphologically complex item, and we apply the same process where we modify the input sentence so that we put all these constituents into it. And as I already mentioned, this is a very useful feature because it allows us to test the model with all sorts of morphological but unattested forms without creating the mappings into the lexicon. So that's one reason why I do it like that. So I hope that this at least gives some idea of how would we begin to approach this topic. And as I already said, it all depends on your theory. How do you think, what kind of elements there are, and how do you think that these mappings work? Perhaps in your model you can also try to avoid this backtracking problem. You can claim that, well, there are some morphological processes which are not really, cannot be structurally ambiguous, cannot be lexically ambiguous. So in that case, you don't need to do derivational search. You could simply map the input word into something always, and then on the basis of what it was that you mapped it into, do some operations to the phrase structure in the working memory. So if there is no backtracking, then you don't need to consider these recursive calls and go carefully item by item. I don't recommend it. I mean, language doesn't have this simplifying property. Okay, let's look now all of this, how it works at the level of the lexicon as I have implemented it now. So here is simple example from my lexicon as it is now. It's just a small segment here, not everything. And this is from the Finnish lexicon. The word here I'm showing is fence, aita. And on the left, and this is a bit confusing now, but I have to, this is always a little bit case when we work with technical materials. On the left, we have the phonological forms that we are expecting to see in the input. So these items here. But the morphing boundary here is always deleted when we are looking at the input. It's here because I want to communicate to myself how I thought this process should go, and also to non-native researchers, how this morphological decomposition on the right matches with the phonological material we have on the left. So this is, I'm making my own morphological theory, underlining theory more explicit by using this notation, these morphing boundary symbols here. But these are deleted from the left side. So that's a little bit confusing, but it's about the technical implementation and not about the theory. So here we have items that we are assumed to be encountering in the input, and any of these forms without this morpheme symbol can be used in an input sentence. And then we have, I use capital letters by a convention for items that I assume do not have morphological decompositions, but they refer to primitive lexical items. And here then in the right side, I simply have a list of features: phonological form, meaning, this is a pointer to its meaning, logical form, the concept of fence. This is not the concept itself, but it's a pointer to the concept. And then via that concept, we can access all the encyclopedic knowledge. What do we know about fences, either more generally or then in that particular context where the conversation takes place. And then I have here non-human. This is regular referential expression. This is about the binding I already mentioned, and the lexical category, and so on. So we give a list of features. This information here is ignored, but as you can see, it's already mentioned as here. I'm using English as a meta language, so the fence here points to the concept of fence. But then I have here aita, which is a partitive form of the fence. And so this item is not associated in the lexicon with a list of features, but with its morphological decomposition according to my own theory or understanding of how morphology works. It is given with this quotation, double quotation, so then it means that this is not read as a feature, but as a morphological decomposition. And here I have the language feature. Currently, every lexical item comes with a language feature. It's just a one way. This allows me to mix if I want words in different languages, but additional ways to have a Finnish lexicon in a different file than English and Hungarian, and etc. Or then in one, or then it could read a title from here. It doesn't matter. So just to point out that this information here goes into the creation of the speaker model, as I already explained. Now, this is the morphological decomposition as I mentioned earlier, the string. And I have several morpheme boundary symbols. The dot means that this is like several pieces of linguistic information in one, coded into one morpheme. Let me take this partitive example, it's more clear. So here we have aita, and then we have a morpheme boundary, and then we have this vowel lengthening, or a or ta. And we have the same regular morpheme boundary here. This symbol is technical symbol that denotes morpheme boundary, not word boundary. And then we have followed by this symbol, which means that the singular, the feature singular and the feature partitive are represented by this one morpheme. So the dot notation encodes this. And the hashtag means that we have here in the original word a morpheme boundary. And then I have an additional symbol for glytic boundary, another symbol for prosodic boundaries. And let me make a comment about this star. I use this partitive star, the star more generally for morphemes that are slightly ad hoc. They have been crafted for some specific purpose and they are not supposed to be completely realistic. So that's why I have two partitive symbols. Par is the symbol for that. Now, what happens then we have this morphological decomposition. All of these items that we discover from this sequence, whatever the boundary symbol, must be such that they are also found from the same lexicon. So the aita, which is the nominal stem or the nominal root item, the content element, lexical content element is here. So the derivational search function will look at this and it discovers the element here when it's processed. And the same with par, star, and partitive, normal partitive case. So this is just elements from the same lexicon, but organized into a what I call morphological chunk, or the morphological decomposition. Now what happens? First of all, if I put this string into the input sentence, the derivational search function or the morphological parser will automatically recognize, okay, this is now decomposition. How it is notifies, because it has this special boundary symbols in it. So this could be just a regular word also. But the system will recognize that it is a decomposition by notifying that it contains these special symbols. So I can't use dots or hashtags now inside of the words, phonological words, without making the assumption that it actually is broken apart into several elements. This is very useful feature that but that I recommend that you make right from the beginning, so that you can really test your model with any kind of complex words without adding them into the lexicon. And you will have to do this when you check it against impossible words, because you don't want to have impossible words in your lexicon. Now what happens when the derivational search function encounters this element which is mapped, or this partitive which is mapped into this? Well, what it is doing is that it will simply substitute this input element with the decomposition, so it knows that this in the input string is actually that element, and then it will then change the sentence, the input sentence, such that it will have these elements as separate items, and it calls the function recursively, so that the next call, let's say, it will see only this item and will discover that, okay, that's a primitive constituent. It will create a nominal lexical primitive constituent with the features shown here. And then it moves on, calls it recursively, and it will find out this symbol. I don't go into this detail, but this is a kind of a minimal nominal head. So we are creating noun phrase and not just a noun. But I ignore this question, it's not relevant. You might not have this in your theory. And so it moves forward. Now, as I already mentioned, you could substitute, and in the final theory, so I believe that our lexicon contains chunks like this. They are shortcuts, memorized shortcuts. But that can't be whole theory because we can decompose new words also morphologically. So if I learn something new, some new word or term for some phenomena, I didn't know that it exists, I can immediately understand words where, if it's a noun, where it has a singular and plural partitive suffixes. And those items cannot be encoded as morphological chunks in the lexicon. So then it's clear that we have also a third process which will able to create these mappings by applying some type of productive morphological parsing. Currently, if I want to test the model with a word that doesn't exist yet in the lexicon, I will have to use the morphological decomposition itself in the input sentence expressions. So let's finally check what happens at the level of my own model. I won't go into too much into details because, as I pointed out, it is a kind of a mixture of legacy thinking and legacy code, and something that I feel is more realistic. So here is the derivational search function I'm currently using. You will notice that the arguments are now keyword arguments. Well, this is a system that when the model becomes more complex, you will probably anyway adopt. And then I'm simply extracting everything out of these keywords. Let's skip further. Circuit breaker is my termination conditions. We ignore that. First thing we have is that we will retrieve lexical items on the basis of what is in the phonological input. So if you have a word like bank, this function will retrieve both lexical items and puts them into a list. The list is here. This takes care of lexical ambiguity. Then we do the branching, as I already explained. So first we check if we are dealing with, if the lexical item we retrieved is actually a morphological chunk, the type of chunk that I just illustrated. Then we parse it, we put it into its elements, and we add those into the sequence, the sentence, and then we simply do a recursive call, don't do anything else. This is what happens here. And the morphological parsing is a separate function. Then in my current thinking is that inflectional features are also processed differently. So, but I decided not to yeah, it's perhaps that I have to ignore this because this involves some issues that I have been recently working with, and I'm not completely sure that everything will work with the real data. But that's just a branching. We go into inflectional morphology, and again there is a recursive call so that we can backtrack if we made a mistake. The next branching condition is prosodic features. I think myself that that's again a different category of input that the brain is processing slightly differently. So there is a branching for that. And then here at the last step, no need to show this all, just to explain what it is that if we found something that corresponds to morpheme that will be mapped into primitive constituent and will be added to the phrase structure in the syntactic working memory. So you see that we have this branching before we do any attachments, and they are all branching recursively so that the backtracking is also possible. And then when we do these decompositions, for example, when the decompositions are added to the sentence, so at some point this recursive function here will receive a morpheme that is a primitive morpheme that maps into primitive constituent, and which will then reach this last step in this branching. And this will enlarge the phrase structure in the syntactic working memory. If the primitive element is prosodic feature, it is handled here in this branch. It will never create a primitive constituent or inflectional feature which are processed their own way, and lexical ambiguity is here. So how does this function handle the situation where some morpheme, the word internal morpheme is ambiguous? So this is the sequence. First, we encounter morphological chunk, we parse it, we add it into the input sentence, all these individual parts. Then we call this function recursively with the new input sentence, and we encounter somewhere along this list the morpheme that is lexically ambiguous. And then here, the derivational search function will recognize that internal morpheme is ambiguous. There are several items that it could refer to, and we add them here into this loop. And then we start looking and branching what these different lexical items could be. And later, if we make a mistake or if we want to do exhaustive search, we backtrack to the same position, to the same loop here, and we start doing the same for the second or third or fourth possible interpretation of that ambiguous lexical, that ambiguous morpheme. Or it can be inflectional affix, or it can be even prosodic feature. This makes it possible to have ambiguous prosodic features. Not unrealistic. So that was basically what I wanted to illustrate in this presentation. As you can see, it takes a little bit thinking, and you clearly see how everything will depend on your theory of morphology. What type of linguistic processing are we ultimately trying to model? and how all of these assumptions can be embedded into the derivational search function.